Everybody, it's video note 7.2. Woo! Percent comp, empirical formulae, and molecular formulae. So here are the objectives. Also, please realize chapter 8 is great. Read it, do it, and then love it. So, what is percent? Percent is always part over total times 100 to make it a percent. So, here's an example for percent. How many people in periods 2, 3, and 4 are Sloth Island wannabes? Well, that would be everybody except the table 3 in period 4 who are the Sloth Island lab team. Okay, so I have 72 students. 68 of them are Sloth Island wannabes. So what is that percent? Well, 94% of students in periods 2, 3, and 4 are Sloth Island wannabes. Part 68 over total. Okay, sloths are cute. Okay, so how are we going to apply this to chemistry? Well, we can figure out the percent composition or the percentage of elements and compounds using the fact that we know that carbon dioxide has 1 carbon atom and 2 oxygen atoms, or 1 whole mole of carbon and atoms and 2 whole moles of oxygen atoms in the chemical formula. So to find the percentage, we just go to the periodic table and say, well, there's 1 mole of carbon in carbon dioxide, and then there's 12.01 plus 2 times 16.00 equals 44.01. There's 44, so the part is 12.01 divided by the total, so, and then multiplied by 100, you find out that this is 27.29% carbon. So by mass, carbon dioxide is 27.29% carbon. Now there's 2 ways you can figure out percent oxygen. You could assume you did this right, and then 100 minus 27 would give you the percent of oxygen. Or you could double check. 2 times 16 gives you 32.00 grams of oxygen in part, that's the part over the total, and multiply 100 to make it a percent. You get 72.71% oxygen. So one way of identifying carbon dioxide is to do the chemical composition of your compound, and if it comes out to these percentages, it's carbon dioxide. All right, and all you need is a periodic table. Okay, what if you get experimental data? You can still do percent, and this way is even easier maybe if you figure part over total again. So here's our total. All right, here's our carbon part, and here's our oxygen part. So we don't need a periodic table now. We can just say, okay, the percent of carbon, the part is the 40 grams of carbon over the total, 95.0 grams total. And then we multiply by 100, and we find out that 40 divided by, sorry, gotta get my calculator out. Hopefully you have your calculators out. Okay. And then for the other one, we do 54.4 grams of oxygen over the total grams. I'm writing a little sloppy here, but forgive me. Okay. So let's see. We got 40.6 divided by 9. 40. Having trouble. 40.6 divided by 95.0. And we get 42.7% carbon, and then this one 54.4 divided by 95 is, I gotta clear that one. You can subtract from 100 to get it too, but then you're assuming you did the first part right. If you do both parts, then you'll find out 57.3% oxygen, which would have came out. But what I want you to notice is that this compound is 27% carbon and 72% oxygen. This one is 42% carbon, 57% oxygen by mass. So these are not the same compound. In fact, this compound is carbon monoxide. So we have 2 different compounds with carbon and oxygen, and we can tell them apart by their percent of each element in the compound. Remember, percent is always part over total. So, what if you had 35 grams of ammonium nitrate? How many grams of oxygen would you have in that compound? Well, here we have to do something a little different. We want the percent. In order to solve this problem, we need to know the percent of oxygen. Okay, so in order to figure out the percent of oxygen, we would have to do percent of oxygen in ammonium nitrate. So we would say, all right, so our part is our oxygen, so we have 3 times 16.00, so percent O, over our total. So we have 14.01 times 2, because there's 2 nitrogens, plus 1.01 times 4, because there's 4 hydrogens, and then plus our 3 times 16.00, because those are 3 oxygens. So we end up with 48.00 grams of oxygen over the total of 80.06 grams of ammonium nitrate. So what this is telling us is that, times 100, is that there is 59.96% oxygen in this compound. All right. Well, if I have 35 grams of the compound, all right, and I know that a certain percent of it times, and I changed my percent to decimal, 5996% oxygen, then 59% of the mass comes from oxygen. So you get 20.94 grams of oxygen in that compound. So step 1, we had to do a percent problem to figure out what percent of all ammonium nitrate is oxygen by mass. Then once you know the percent of oxygen, you can figure out, well, in any sample of the compound, 59% of it will be oxygen. Okay. So that's good for figuring out how, if you need a certain element in, you want to decompose compounds to get it. Okay, empirical formulae. The reduced formula of any compound is its lowest whole number ratio of each of the atoms in the compound. It's called an empirical formula. Okay, so here's a compound, C6H12, but its empirical formula would be reducing those subscripts. So we found CH2 is the empirical formula of C6H12. So it's the reduced formula. Water's formula is H2O. What is its empirical formula? Well, already our lowest ratio is 2 atoms of H to 1 atom of O. So its empirical formula is also H2O. So some compounds, their empirical formula is their molecular formula. Other compounds can be reduced from their molecular formula to their empirical formula. But what we're going to do next is we're going to figure out how we can figure this out given data. Okay, so how do you find an empirical formula? Well, you need to find the subscripts. So we need to find out this is a 2 and this is a 1. How do we do that? Well, each of these subscripts represents atoms. But instead of counting 2 atoms out and 1 atom of oxygen, it's really, we can say 2 moles of hydrogen and 1 mole of oxygen. So moles can be our key to figuring out empirical formula. So the key is always go through moles. Let's do an example. Okay, so first, here's just a step checklist if you want to have one. But use the grams given in the problem, or use percent as grams and convert to moles using the periodic table, and then get the moles into whole numbers by dividing by the smallest. Anytime you want a whole number, you take the big one divided by the small one. Okay. Then you multiply by 2 or 3 if needed. Usually you'll get whole numbers or close to whole numbers. So let's see what this means. I'm telling you the composition of a compound. Here's me telling you 40% sulfur, 60% oxygen by weight. Okay. We'll put a few decimals in there so that we can be a little more exact. What is the empirical formula of this compound? So what is the lowest ratio of sulfur to oxygen by weight? Well, these are percents, but you can use percents as grams. Because if you have 40%, if you had 100 grams, you have 40 grams. So 40 grams of sulfur times, we want to change, we got to go through moles. So we say 1 mole of sulfur, and we go to the periodic table, we get grams, 32.07 grams. So we figure out that, I gotta get my calculator. We find out that 40 divided by 32.07 gives us 1.2 moles of sulfur. Okay, and I'm just going to write under here 1.247, just for a few more digits to help us later. 60 grams of oxygen, and we're going to say, well, each gram, 16 grams of oxygen for every 1 mole of oxygen. We find out that 60 divided by 16 is 3.8 moles of oxygen, which is 3.75. Okay, now we still need to find out the mole ratio of sulfur to oxygen to get the empirical formula. So what we have to do is pick the bigger one and divide it by the smaller one. So oxygen is going to be 3.8 moles of O divided by the 1.2 moles of S. And so, because we divide by the smaller one, 3.8 divided by 1.2, and we get close to, and you know what, I'm actually going to use the drawn out values, 3.75 divided by 1.247, and I get 3 equals 3. If I take 1.2 moles of sulfur and divide by 1.2, so actually the bottom number is really just a divisor. Sorry. And so this is equal 1 mole of S. So 1 mole of S, 3 moles of O. And so if a compound has a ratio of 1 mole of S to 3 moles of O, that compound is SO3. Okay. So that's the empirical formula of that compound. Let's do another one. Pure formaldehyde is 40% carbon, 6.7% hydrogen, 53.3% oxygen. What's the empirical formula? Well, first step is we have to use moles. So we can pretend we have 100 grams. So then we have 40.0 grams of carbon, okay, 53.3 grams of oxygen, and 6.7 grams of hydrogen. But in order to do an empirical formula, we need these in moles. So grams of carbon to moles of carbon. Where am I going to go get the grams? From the periodic table. Alright, grams of oxygen, 1 mole of oxygen. Go get 16.0 grams. 1.01 grams of hydrogen. Thank you, periodic table. 1 mole of hydrogen. Okay, so then we're going to figure out how many moles we have. So 40 divided by 12.01 gives us 3.33 moles C. Okay, 53.3 divided by 16 gives us 3.33 mole O, and then 6.7 divided by 1.01 gives us 6.6 mole H. Alright, so we're not done yet. You can probably see the pattern here, but you take the smallest number given and use it as a divisor. So this is going to be divided by 3.3, so it's going to come out to 1 mole of carbon in our compound formula. The 3.3 is a divisor, so we also have 1 mole of oxygen in our compound's formula. 3.33 is a divisor, it's going to come out to be 2 moles of hydrogen in the chemical formula of our compound. I'm sorry, the empirical formula. So how would we write this? Well, we have a C, we have an O, and we have 2 H's. You can write it as CH2O. You can write it as OCH2. You can write it in any order. So you could do that. All of these 3 would represent empirical formulas because it's the lowest ratio of moles in that compound. Okay, here's another empirical formula problem. All right, so we start with the grams of carbon, and we change it into moles. 12.01, go through moles, grams of C for 1 mole of C, and we get 6.24 moles of carbon. And then we do the same thing with the grams of hydrogen, and change it to moles. What we're doing here is we're saying, well, I know that the empirical formula is the lowest whole number ratio of moles. And so then once you know that, you take the grams and change them to moles, and then you have to get it to the lowest whole number ratio, you have to use the smallest number of moles as a divisor. So we find out we have 1 mole of carbon, and we divide by 6.24 here. So after you figure out which is smaller moles, you just take that number and use it as a divisor to get it into whole numbers. And this comes out to be approximately 4 moles of H. So most of the time these will work out to whole numbers, but if they don't, you could just multiply them by a 2 or a 3. Okay, so the empirical formula is CH4. So this compound's empirical formula has a ratio of 1 mole of carbon to 4 moles of hydrogen as its lowest whole number ratio. Okay, so that was empirical formulas. This is now called a molecular formula, and a molecular formula is the identity of the compound. Okay, so for example, water's molecular formula is H2O. That's the identity of water. It's also empirical because it's the lowest ratio. Okay, hydrogen peroxide is H2O2. That's its identity. Okay, now the empirical, so this is called molecular because that's the exact formula of the molecule. Okay, the empirical formula for hydrogen peroxide is actually HO because you can reduce those. Molecular is what it is. Empirical is the lowest ratio. Sugar is C6H12O6. That's its identity, molecular formula, counting C's, H's, and O's in the compound. The empirical formula is CH2O because this is its empirical formula. Okay, so how can we get molecular formulas? Well, here's how you do it. The molar mass is the mass of the molecule. Okay, so if we want the molar mass of water, we have to use molecular formula, add it up, periodic table, add it up, periodic table. Okay, so molecular mass is the mass of the exact molecule. It can be given in the problem, or you can calculate it, okay, by the information given. The empirical formula mass is the mass of the empirical formula. So you either go to the periodic table to get it, or you do the empirical formula problem. And then what's the difference between those is a multiplier. Okay, so the molecular mass divided by the empirical mass will give you the amount of times you multiply the empirical by molecular. What I mean is this. Okay, they're telling you empirical, so this is the lowest ratio, but the molecular mass is 112.16, so that's the exact mass. Find the molecular formula. Okay, well, we would say the molecular mass, the molecular formula mass, mass is 112.16 grams per mole. Then we need to divide by the empirical formula. Empirical formula mass. So how would we get that? Well, here's the empirical formula. CH2N. The mass of the empirical formula is 12.01 for carbon, 2 times 1.01 for hydrogen, and 14.01 for nitrogen. So you'd add that up. Okay. 12.01 plus 2.02 plus 14.01 gives us the empirical formula mass is 28.04 grams per mole. So if we divide those out, 112.16 divided by 28.04, we get approximately 4. So the empirical mass needs to be multiplied 4 times to get the molecular formula. So we need to take the empirical formula and multiply it 4 times. So we get 4 moles of carbon, 8 moles of hydrogen, and 4 moles of nitrogen as the molecular formula. Alright, let's do another one. Okay, so in order to get a molecular formula, to take the formula mass of the whole molecule divided by the empirical mass, you get a whole number, and then multiply that whole number times the empirical formula. Okay, so earlier we had this 25 grams, 75 grams of H, and we found out that the empirical formula of that was CH4. Okay, we calculated that out, CH4. All right, so this is the molecular mass. So we take molecular formula mass divided by empirical formula mass. And so the molecular formula mass is 80.25 grams per mole. Given in the problem, look, given, I got it. Empirical formula mass is the mass of CH4. So 12.01 plus 4 times 1.01 equals 16.04. So we divide by the mass of the empirical formula, and I think it's 16.05. Who does that? Okay, grams per mole. We find out that the multiplier is 5. Okay. So what does that mean? That means CH4 is empirical, so 5 times that, C5H20, is molecular. All right. So empirical formula gives us the lowest ratio of atoms in the compound. Molecular formula is either the same as that or some multiple of it. How do you figure it out? Well, you need the mass of the whole molecular formula divided by the mass of the empirical formula, and you get a multiplier. And then you multiply, okay, times 5 to get that. Okay, so why do we even care? Well, if you find the empirical and molecular formulas of substances, then you can decide what they are, and you'll have a better chance of seeing what they look like. So we had two. We had CH2O, which was the empirical formula of formaldehyde. Formaldehyde. And then later, we had that same empirical formula here, right? But is sugar and formaldehyde the same thing? No stinking way. Okay, so if we know empirical and molecular formulas, so see, this is also CH2O, but these are very different because sugar is a ring structure with the 6 carbons, and formaldehyde looks like this. So now I know you want to take organic chemistry so you don't get these two things mixed up, because this one is a preservative and this one runs your body. It's fuel. So anyway, make sure you know that percent is part over total. Always go through moles. Empirical is the reduced formula. Molecular is the real formula. And the relationship between them is a whole number multiplier. Okay, chapter 8 is great. And peace out.